Welcome. Today we're going to talk about point groups. So we already talked about symmetry elements last time and their operations. And so basically molecules are classified into groups based on their elements and operations. And so before we go into the specific groups, there are a couple things that are characteristics of groups. And again, this is from the mathematical treatment. So if the operations A and B are members of the group, and the operation A, B equals C, then C is also a member of the group. And so we looked at, for example, ammonia. So if we have our top-down view, we could think of that as a triangle. And so we have our C3 axis in the middle. And then we have some mirror planes. And notice the prime is just to separate the three and show that they're distinct. And so in ammonia, the operations we have are E, C3 once, C3 twice, sigma V prime, and sigma V double prime. And remember within this that our operators don't commute. So again, what this means is, remember in this notation, we always do whatever's to the right first. So B and A does not equal B, A, B. So if we, for example, do for ammonia, C3 and sigma V, I'm rotating the triangle this way, 1, 2, 3. We do sigma V first because that's to the right. Three and 2 will flip. Then we do C3. And so if instead we had gone directly from here to here, this would have been our sigma V double prime. So a different one. And so what this means is that this is also in the group. So we know that C3, or sigma V, then C3 equals sigma V double prime. Second rule, the group must contain E. So we kind of talked about this. Three is A, B, C with parentheses in that position is the same as if we do this. So this means that the associative laws hold. 4, every member must have an inverse. So the easiest one to think of is that the inverse times the inverse equals E. So basically something that when it's multiplied by that equals E. For a C rotation, CNM, it would be C to the n minus m. For sigma v, again, it's just itself. For S, remember it depends on if it's even or odd. So if it's even, it's the same rule as for rotation, but if it's odd, it's now 2n minus m in the superscript. And that comes out of the derivation we did last time. Within these groups, we also have something called classes. So A and B are conjugates if they are related by a similarity transform. So if, for example, we have p to the minus 1 times A times P, and that equals B, then P is a member of the group. So if we look at an example, what is the conjugate of C3? So if we have sigma v minus 1, C3 sigma v, we're going to find out what that equals. So we're going to start with our same triangle. Going to do our sigma v first. Then we're going to do our C3, just like before. And now we do another sigma v. So remember, this is the inverse of sigma v. And net, this would be the same as if we did C3 2 times. So the conjugate of C3 is C3 twice. So they are in the same class. So what that means is that they generally get grouped together on what we call a character table, and we'll talk more about that later. So if we look at ammonia again, I'm going to draw it as a triangle again, just because that'll keep things consistent. So for ammonia, we have E C3 twice, C3 once, sigma V prime, and sigma V double prime. But within that, those are all the operations. But we divide them into classes. So it has a total of 3 classes. So the classes are E, 2 C3, and 3 sigma V. And then the 3 classes make up a molecular point group. And the point group is represented by a Schoenflies symbol. And so in the case for ammonia, this is called C3V. And so now I'm going to go through all the different groups, and then after that you'll learn how to assign groups for specific molecules. I won't go through absolutely every group, but I'm going to go through most ranges. So some have one symmetry element. We've talked about this one. So this only has E, so everything has E. And so basically if we have, for example, this copper complex that has 4 different substituents, the point group is called C1. So that, if you can't find any symmetry, is what it'll be. Some have 2 symmetry elements. So if we have, for example, E and a mirror, so this would now be, for example, this complex. So here we're drawing it as square planar, so that means that it's flat. So your sigma is in the plane of the paper. And so this would be a CS point group. The next one, if we have E and inversion, such as this molecule, then our point group is C sub I. If we have E and a C rotation, C sub N. For example, a peroxide, here we just have a C2 axis. And so the point group will be C sub N. So for this particular molecule, since it's a C2, it'll be C2. So you can see the number comes from the axis. We can also have E and an SN. I'm going to refer you to Otterbein's website. To see examples of this. So you can imagine this is not very common. One note on this is that S2 does not exist. And so the total group is S sub N. Then you can imagine it's actually far more common that we have more symmetry elements. And so the last class have many symmetry elements. So if we look at, for example, C and H, this would be E, C, and sigma H, S, N prime. So one example is this boron ring. And you'll notice sometimes it depends a bit how you draw a molecule. So when we look at molecules, we usually assume the most symmetric. So this would be C3H. So remember the sigma H in this case will be in the plane of the paper. In this case, our highest rotation axis is a C3 right in the middle. A pretty common one is C and V. So V is now that we have a vertical mirror plane. So ammonia, for example. So this would be a C3V point group. Remember our C3 axis is up here. Sigma V is going through kind of one side. So there's one of them is in the plane of paper. We also have D sub n. So D means that it has a Cn rotation, E, and it has a perpendicular C2. This is also quite common. So one of the common examples of this are what we call propeller shapes. And so here, if you look at this, this is just implies a ligand. So it's some connection that's less critical. So in this example, this would be D3. We also have DNH. So this now has ECN. Perpendicular C2, sigma H, sigma V, and sigma D. So D stands for dihedral. Usually this is between bonds. So if you've already found two mirror planes, then you add in a dihedral. So usually this is through atoms. So some common examples, so here, this is D3H. So we have a C3 perpendicular. We have a sigma H in the plane of the paper. We have sigma V's here. And then we also have perpendicular C2 along those sigma V's as well. Another one that we've spent some time looking at is ferrocene. Eclipsed. So this is D5H. We also have D and D. So this has ECN, perpendicular C2, sigma D, and S2N. So here, for example, your ethane. If we look at it in terms of a projection, it might be easier to see. So this would be a D3D. We also have C infinity V. So this is for linear. So you have C or ECN sigma, and your CN is actually an infinity. So there's no real axis. So basically HCl, for example, says heteronuclear diatomics. We also have D infinity H. So these are for linear molecules. So if you have a linear molecule, always check this first. So C infinity perpendicular C2 now, since it's a D group, H, V, and I. So for example, CO2. And then we have some pretty symmetric ones. So this is one you should also be able to just see by inspection. So TD, EC3, C2, S4, sigma D. So this is tetrahedral. So basically, if you're comfortable looking at tetrahedral from VSEPR, you should be able to identify this pretty readily. So methane, for example. And then the last one that's also, again, these are very common and very important. E, C4, C3, C2, S6, sigma H, and I. This is our octahedral. Again, from VSEPR, become comfortable just identifying octahedrals as is. So this is generally how I would draw an octahedron. It also can be drawn from a slightly different rotation, so just so that you've seen it and don't get confused. This would be another way to draw an octahedron. And then there's some other rare groups. For example, IH, which is the buckyball, or TH, you really won't encounter these in many situations. So again, use the Otterbein website to look at these. And just to leave on the last note, how do we determine these? And the answer is we use a flow chart, and you're going to have to memorize this. I realize that in this class you'll have open notes effectively since we're remote, but if you aren't comfortable with it, then you're not going to be very fast and it'll cost you a lot of time. So once you start doing some practices, it actually becomes quite second nature and you'll find it quite easy. So the way you're going to practice this is using the Otterbein Symmetry Challenge, and it guides you through going through these point group exercises. So that's it for this lecture. Thanks for listening.